Yes. So my talk already will be on. We start. Okay, that's my. So we already start teaching. So I will be just speaking about two quite basic techniques in parameterized algorithms. Both techniques are very simple. One is a bounded search tree, or it's also called as a branching. And I will give examples how to do branching for vertex cover, several algorithms for tree heating set, and then also talk a little bit about feedback vertex set in tournaments. And then I will speak about the second technique, which is also quite basic and quite simple and nice, called iterative compression. And there I will give an improved algorithm for feedback vertex set in tournaments to running time to the k. And also I will speak about tree heating sets. Okay, so these two techniques are very simple, very basic, but because they are very simple and very basic, if you combine them with other techniques, this is basically what you have to try first. When you see a new problem, try to do these two techniques. If you fail, try to do something more clever. Okay, bounded search trees. So what's happening here? I just start immediately from example. Vertex cover, again, our favorite problem. During this week, you will hear a lot about vertex cover. And why vertex cover? Well, it's our favorite problem, but why it's our favorite problem? It's perhaps it's the first interesting, complicated problem, which is extremely simple. So basically, it's the simplest problem out of all. Now, what is vertex cover? Once again, I have a graph, I have an integer k, and I'm asking for a set of vertices such that after I remove these k vertices, I will get an independent set. Or in other words, the minimum number of vertices hitting all edges of the graph. Yeah. So what is the main observation behind the algorithm for vertex cover? No, just a second. Yep. So what is the main observation? So if I have an h, u, v in a graph, then every vertex cover should contain at least one of the endpoints of that h, right? So the h should be heated. Okay, so in other words, if I have a g, k, which is a yes instance of a parameterized version of vertex cover, then this is a yes instance if and only if either so this happening or this happening, right? So either one vertex is in one of the endpoints is in the vertex cover, so then I can put this vertex into vertex cover and decrease the parameter by 1, or I can take the second vertex into the vertex cover and decrease the parameter by 1. So this is what's happening here, and this gives me immediately the following branching algorithm for vertex cover. I have, once again, I have a graph. G, I have an integer k as a parameter, and then I check. If my parameter is less than 0, I cannot have a vertex cover of size -1 in this graph, right? Something goes wrong. I say no. Okay, if my graph has no edges and k is non-negative, means that, yes, I have a yes instance, that's fine. Or the third possibility, if I have an h, I try to branch on this h. So what I am doing, I say, okay, I consider two subproblems. In one subproblem, I put one endpoint u of the h in the solution. And in the second subproblem, I put the second endpoint of the h into the solution. So I branch on two subproblems, and I also decrease the parameter by 1, right? Because I'm using my budget to put this vertex into the vertex cover. So this is just a recursive algorithm. Okay, so how to analyze the running time of this algorithm? There is a quite useful viewpoint for all this type of algorithms. Just view the algorithm as a branching tree. So basically, nodes of the tree corresponds to the subproblems, and basically the number of subproblems we need to solve at the end is proportional to the number of the vertices in this tree. And this is a binary tree, so usually, in the example for vertex cover, it was a binary tree, and basically this means that the running time of the algorithm up to some polynomial factor is proportional to the number of leaves in this tree. And how to analyze the number of leaves in this tree? Well, we have a binary tree, so every time we branch on at most two problems, the height of the tree is at most k, so this tree has at most 2 to the k vertices, which means that the running time of the algorithm is also 2 to the k times some polynomial of n. Yes. Okay, that's so far so good. But even if we look at a very simple example, right? So when this algorithm, when the running time of this algorithm is tight, right? Well, this is the simple example when if I start performing this algorithm on a graph which consists of k matchings, then the running time of my algorithm will be exactly 2 to the k. Right? For every matching, I have exactly 2 options, k matchings, 2 to the k. Yes, that's true, but on the other hand, this is a kind of a simple and trivial instance, right? So if I have a graph which consists of k matching, I can do it easily in polynomial. Well, I can do it even faster than in polynomial time, right? So it's like I can give you immediately the solution. Okay, so and actually more generally, if I have a graph where all vertices are of degree at most 1, I definitely can solve my problem in polynomial time. So. Okay, so let's try to do once again branching arguments, but a little bit differently. So what I'm doing this time? So suppose I have a vertex in a graph of degree at least 1 now. Then if what's happening? So there is a vertex and there are some edges incident to this vertex. I have to hit the edges by the vertex cover, either by this vertex or by its neighbors. Right? So, and if I put a vertex, so it means I have to either put a vertex in the vertex cover, or if I don't put the vertex in the vertex cover, I have to put all the neighbors of the vertex in the vertex cover. Right? So this is what I'm saying here. This gives us another type of recursive algorithm. So what I'm saying here, so either I am taking the vertex in the vertex cover. So I remove the vertex from the graph, I decrease the parameter, and I work with a smaller problem. Or I don't take the vertex in the vertex cover. What I'm doing in this situation, well, I have to remove the vertex itself. So here it's, and also I have to remove all its neighbors and put all the neighbors in the vertex cover. Okay. Yeah. Okay, so this is the idea of the algorithm. And so what the algorithm is doing is almost the same thing. If my parameter is negative, I say no. If I have no vertex of degree at least 2, then I solve the problem in polynomial time. Otherwise, I find a vertex of degree at least 2, and I try to branch on this vertex. So I call my algorithm recursively. So here is a tiny mistake. So here I should remove not the vertex from the graph. I should remove. I should not remove the open neighborhood. I should remove the vertex itself and its neighbors also, right? From the graph. Okay. So what is the running time of this algorithm, right? So if I just try to upper bound the running time of my algorithm by some function t of k, the function of parameter, then more or less this. So how this function behave, right? So in one case, in one case I decrease the parameter by 1, right? This corresponds to the case when I remove the vertex, and the second case when I remove the neighbors of the vertex, right? And yes, this is happening if the parameter is at least 2, and if the parameter is 1, then so I would say the running time of my algorithm is constant. Okay, so then what's happening here? So if there's a standard way of analyzing this type of recursions. So I'm looking for the solution in the form of the exponent. So t of k, I bound some constant c times lambda k. And then, so if I doing this, I write my so I write my function t of k. Then this recursive systems transform into this system of into this inequality, and basically what I'm doing here, yes, so far so good. So and then basically, what I happen, so for the vertex cover, this corresponds to the following situation. I have I'm looking for the function of order alpha k minus alpha power k minus 1 plus alpha k minus 2, and my condition is that all this should be at most alpha power k. Okay, so what's happening here? I just divide by k minus 2 here and here. So here I have alpha lambda square, and here I have lambda, and here I have 1. Right? So this is what I did. And now, yes, I have to still do some work. I still have to solve quadratic equation. So if I solve the quadratic equation, well, it should have 2 roots, right? One root is negative, doesn't make sense to me. One root is positive. Okay, this is 1 plus square root of 5 over 2. So what is this number? No, just if you are alive or not, right? Still, or
it is the golden ratio, Professor.
Yes, thank you. Thank you. No, just okay. Yes, okay. Yes, and so basically this means that the running time of my algorithm. So not the running time. So the recursive function t of k is at most is at most the golden ratio power to the k, right? Okay, but still, things were quite simple, so I almost did nothing, right? So, and obviously, why I decided to start from the simple algorithm? Because also it gives us brings us to very natural questions in parameterized algorithms. I have an algorithm, not only in parameterized algorithms, in any types of algorithms. You have an algorithm, can you get a better algorithm with better running time? Right? So can we get a better algorithm here? Definitely, right? So what's happening here? If I have a graph where all vertices are of degree at most 2, what does it mean? Every connected component is either a path or a cycle. I still can solve the problem in polynomial time. Well, if you are, unnecessary educated, you can say, oh, every graph here has of trivets at most 2. I solve them and do an algorithm for graph of bounded trivets. But if you are just smart, you can say, okay, anyhow, if I know how I can solve vertex cover on a cycle, right? I just can do greedy type of procedure, do it. Or I also can know how to do it on paths. So if my graph has a degree at most 2, I can solve the problem in polynomial time. So then what I do just the same argument I had for degree 1. So the only difference is now that now I'm gain slightly better in this problem. So once again, so what is my algorithm? Once again, I branch into subproblems. Either I put one vertex into vertex, either I put my vertex into vertex cover, or I put it neighborhood in the vertex cover. But now I branch in a vertex of degree at least 3, so I put at least 3 guys in the vertex cover. So I decrease my parameter by at least 3. Good. So this brings me to the, so if I estimate the function t of k, this has something like lambda cube is equal to lambda square plus 1. Well, we still can solve this equation analytically, but not me, probably. So usually you use Maple or a MATLAB or write your own program to solve this type of problem. Yes, and believe me here, so the running time of this algorithm will be 1.46 to the k. Okay, so again, so simple, so good. Can we do something better? Okay, so so here I already have a problem, right? So my argument was, if I have a graph with all vertices of degree at most 2, I can solve the problem in polynomial time. But if all vertices of my graph are 3, vertex cover is already NP-complete there. So I cannot continue this type of arguments anymore. I have to do something smart, but then definitely it's not the end of the story. But 2 questions are really interesting. The first question is, well, if so the bound I give for vertex cover is tight, what I mean by that? Well, I have, first of all, I bound the function t of k. I have some recursive function, and I say, well, this recursive function is bounded by some exponent of k. This bound is up to polynomial factor, it's tight, it's easy to see, right? But somehow, the more interesting question is, I have some branching procedure, But the running time of this algorithm, is it really tight or no? Because if you start to look carefully at what's happening in my branching algorithm, well, I have a vertex of degree 3, for example. I remove it. But it's not just I remove the vertex or I remove its neighborhood. I also change the structure of the graph. For example, I can create a lot of vertices of degree 2 or of degree 1. So, and how to analyze this type of things? Things become very messy and quite complicated. So we still don't know or any way to analyze branching algorithm so exactly, or to give a really tight running time of branching algorithms. Yes, and basically, so if you want to improve this running time up to this here, or even a little bit like from 4 to 3, it's still probably doable within few hours. You just have to be a bit more careful to look what's happening if you remove vertices of degree 2, how this changes the structure of the neighborhood, and do the right assumptions. But there is a much more complicated ways of doing branching algorithms, and basically, so the best known algorithm for vertex cover is this 1.2738, and this due to Jenier Chen and Ija Kanch and Xie. This is the algorithm. Yes, but more generally, so if we speak about this type of recursions, so how to solve this type of recursions? It's again, it's the same general, or so the basic approach. So I'm looking for, so if I have a recursion, now in this recursion, I'm branching not in two subproblems, but I branch in P subproblems, and in every subproblem I decrease my parameter by D. So then again, so I can analyze the running time of this type of, or the size of this tree, branching tree, by making use of this inequality, which brings me to just finding the root of this characteristic polynomial. Okay, so again, it's not so important, but actually this type of polynomials, they have a unique non-negative root, and basically this unique non-negative root corresponds to the base in the exponent, which estimates the size of the branching tree. And so the root of this polynomial it depends only on the numbers d1, d2, dp. That's these numbers. They are called the branching vectors. And sometimes it's not it's not important to know how the branching vectors are by heart. So what are the branching vectors? But somehow the behavior of these branching vectors are quite non-intuitive, and it's so the only way I know is just really to look at them and to compute them. What I mean is very non-intuitive. For example, you have two branching algorithms, and one algorithm has a branching vector 1.4. So one problem parameter decreased by 1, and the second problem parameter decreased by 4. And the second subproblem is branching vector 2 and 3. Which one is better? No, yeah, but so which one is better? I can tell you, yes. I also can tell you, right? So, okay, so 2.2 and 3. 2 and 3 is 1.3248, and 1.4 is 1. So 2.3 is better, right? But what is better, 2, 5 or 1, 4? Okay, anyhow, so this is at least yes, at least if you have a branching algorithm which uses two branching vectors up to 1 to 5, you can just check in our book. It's there, so it's you don't have to write your own program for that. Okay, so another example of branching algorithm is a heating set problem. So heating set problem is the following. I have a universe of elements, U. I have a family of sets. Each set is bounded by D. D is some universal constant. And I have an integer k, which is the parameter. And then I'm asking if there exists a subset X of U, of size at most k, such that which hits all the subsets from my set. So for example, here I have an example with 4 sets. Each set is of size 3 exactly. And then heating set here is white. It's B and G. And I cannot find heating set here of size 1 also. Okay, once again, so heating set is a generalization of vertex cover, right? So essentially, it's a generalization of vertex cover, right? So so vertex cover is more or less the two heating set, right? If I look at the edges of the graph as pairs of elements, this is the heating set. Okay, so once again, what we were doing for vertex cover, we were taking an edge, and we were deciding on the endpoints of this edge, which of them goes to vertex cover and which doesn't, right? I want to do exactly the same for heating set. But now I have an edge which contains 3 elements, so I am, oh yes, this is, so then what I'm doing here, I pick up an hyper edge of 3 elements, and then I just call recursively. I know that at least one of the elements of this hyper edge, it should be in my heating set. So what I'm doing, I just branch on 3 subproblems, and in each of subproblems, I guess which of the elements goes there. Okay, and when I guess which elements go into heating set, what I'm doing, I also remove all sets which contain this element, right? Because they already are hidden. So this is the algorithm, and the running time of this algorithm, okay, the same arguments. I have a ternary, right? No, ternary is 3. Ternary and quadro, okay. I have a ternary tree, right? So every vertex is of degree 3, except leaves, and the height of the tree is k, so I have 3 to the k algorithm solving this problem. Okay, and another example. Actually, now already I'm preparing the ground for my next topic, iterative compression. So I will give you this algorithm. This algorithm, there's no algorithm actually here. So what's happening here? I have the following problem. I have a tournament. So tournament is you take a click or a complete graph, and you add directions to the edges, right? That can be. Okay, so I have a tournament, and I have an integer k, and then I'm looking for a feedback vertex set in this tournament. So what is the feedback vertex set in this tournament? Is a set of vertices x, such that when I remove the set of vertices, the tournament will become acyclic. In other words, I'm looking for a set of vertices of size at most k, which hits every directed cycle in the tournament. So here is example of the tournament, and here is example of the feedback vertex set of size 1, because, if I remove this vertex, there will be no directed cycles in this tournament. Yeah, I check it, but we always, yeah. Okay, so the main observation here, so which is sufficient for the algorithm, is the following. My tournament is acyclic if and only if it doesn't contain a directed triangle, right? And the proof is, by example. Okay, suppose I have a directed cycle there, right? Because it's a tournament, every pair of vertices should be adjacent there, right? And then if I have a directed cycle, well, I have a chord in this cycle, and then where this chord is directed. If it's directed in one direction, I can find one cycle inside of this cycle and the other. So then my arguments will be that, okay, if I have a tournament which has a cycle, but yes, yeah. No, this proof is so simple that yes, you can lose in this proof. Okay, once again, so what I'm saying that every directed cycle contains a directed triangle, right? That's what I'm saying here. So which means that basically, if I want, so my feedback vertex set in tournament is exactly triangle heating set here. And now if I view every triangle as an instance of 3 heating set problem, I will have my 3 to the k algorithm again, right? So feedback vertex set is exactly the same as heating directed triangles. Directed triangles are the same as 3 heating sets, and so this gives me running time 3 to the k. Yes, so that was a very brief overview of all of branching algorithms. There will be more branching, not done by me, by some other people, more clever branching. So branching is not always so simple and naive. So there are good ideas there happening there. Yes, and also if you want to just to warm up, and if you never did branching before, try to do these problems yourself. The first one is cluster vertex deletion. What is a cluster graph? Cluster graph is a disjoint union of clicks. And now the problem is I want to find at most k vertices such that when I remove these vertices, my graph will be a cluster. Right? This is the first exercise, and the second exercise is a bit more tricky. So here I'm asking, so the running time of my algorithm will be something like k to the k. And this is a minimum fill-in problem. What is this? I have a graph, and I want to add at most k edges in my graph, such that my graph will be chordal. And chordal means that if I take any cycle of length more than 3, this cycle should contain a chord. So there's no induced cycle of length more than 3, in other words. So this is another interesting problem. So how to do branching algorithm for this problem is also a nice exercise. So any questions about branching so far? Yeah. Okay, then I go to another, also very basic and also very nice technique, which is called iterative compression. So iterative compression. The question here is, or what's happening, so the iterative compression is a combination of two simple ideas. So one simple idea is the following. Suppose I give you solution which is not optimal, but close. Say I give you some approximation, right, for example, of my solution. Will it make my life easier to find the optimal solution if I already have some slightly oversized solution? Right? And sometimes yes is the answer. And let me just, again, I will give you an example with my favorite problem, vertex cover. So first of all, this example doesn't make much sense because the running time of the algorithm will be 2 to the k, and we already have a much better algorithm for that. But for educational purposes, it's a perfect example of how I will do compression. Okay, so I have a vertex cover of size k plus 1. And how can I find a vertex cover of size at most k? So once again, this is the situation, what's happening here. I have a graph. I have a vertex cover in the graph of size k plus 1, and I have remaining vertices. And the remaining vertices, they are independent set. Right? So what I'm doing, I guess. I guess which part of the vertex cover will be a part of the new vertex cover, and which part is not. Well, so I have a size set of size k plus 1, so I'm doing 2 to the k plus 1 guesses, but so far I'm happy with that. Okay, but when I made a guess, the things become easier. Because what's happening? I guess which part of the vertex cover will be the part of the solution and which part will not be. Well, the part which will be the part of the solution, I can safely delete these vertices and decrease the parameter. They're there. And the second guys, which never go to vertex cover, they also actually they provide me a lot of information what happening to what happened to my solution. And actually, I can solve this problem after I did my guess. I can solve the problem in polynomial time. So why this is polynomial time? Well, these are the vertices which will go in vertex cover. I remove them. These vertices they never go to vertex cover anymore, which means that every edge which remains after I deleted these guys, it should be covered by someone from the right. So actually, I should take all edges and I should take all these endpoints, and that's the only way for me to do the vertex cover. Right? Now this I can clearly do in polynomial time. So this gives, again, the algorithm of running time 2 to the k, if you give me a vertex cover of, say, k plus 1. So this is one trick, and I will be exploring this trick many, well, not 2 times, once again, so that will be the same type of repetition. But how...
I don't understand. I know this algorithm, but I don't understand the story you're telling me. So S is... Which mindset should I be in? I know that S is a vertex cover?
Okay, so once again, I give you the set of size k plus 1, and I tell you this is vertex cover. Now, can you give me vertex cover of size k? What you do, you guess which part of this set S will go to your new vertex cover, and which don't. Right? The set which goes to vertex cover, you delete them, and then you take all other non-isolated vertices to the right, and you say that this is your vertex cover. If the size of this is at most k, fiesta. If not, you say no, you're also happy.
Can't you have another vertex cover of size k which is not a subset of the original one, couldn't be such a graph?
Yes, but I guess all possible subsets. So I also guess empty set, also subset. I really guess everything. So this case also will be covered by all my 2 to the k guesses, if I understand your question correctly. Okay, but who on earth will give me the vertex cover of size k plus 1? Well, for vertex cover, I can use run polynomial time 2k approximation algorithm and use this. But there is also a very nice trick, and this is the second trick. And when I put these 2 nice tricks together, I will have a technique, right? So this is the following. It's called iterative step. So what's happening here? I just take some ordering of the vertices of the graph. And then I start with a graph which is induced by the first k plus 1 vertices. This graph has k plus 1 vertex, which means that the vertex, I also can find easily vertex cover of size k plus 1 in this graph, right? I take everything of this graph and I say, this is the vertex cover. Now, what I'm doing, for this graph, I perform my compression algorithm. Now I have a graph with vertex cover k plus 1. I find a vertex cover of size k, or I can say that there's no vertex cover of size k. In the last case, I just say no, there will be no solution at all. Or I find a vertex cover of size k, and then what I'm doing, I just add one more vertex. If I have a graph already built on p plus 1 vertices, I add one more vertex to this graph, and I also add this vertex to the vertex cover of size k. Now I have a vertex cover of size k plus 1, and I can proceed again. I do compression. So then what I'm doing, I'm iterating. So every time I'm adding a new vertex to the vertex cover, I build a larger graph, I compress, I build a larger graph. So I do at most n steps, and at every step, I run my compression algorithm. That's why the technique called iterative compression. Right? Let's try to see what we can do for feedback vertex set in tournaments. Once again, we have a tournament, and I want to find a set of, decide if there is a set of k vertices which hits every directed cycle here or every directed triangle here. Okay, suppose we have a feedback vertex set of size k plus 1. How we can find a feedback vertex set of size k? Well, I will pronounce the whole thing once again, but after that I will be jumping over these cases. Okay, so what's happening here? So again, exactly the same thing with vertex cover. I have my feedback vertex set of size k plus 1, and I do 2 to the k guesses which guys from this set will remain in the feedback vertex set and which guys will not be there. Okay, so far for this type of guesses, I still spent 2 to the k running time. And so I already have some set of vertices which I say that they should be in the feedback vertex set. So these guys I can safely remove, decrease my parameter by the number of the guys I remove, right? And then what remaining, or what the problem boils down, is the following problem. I have a tournament with a feedback vertex set W of size P, and then I'm asking whether my tournament has a feedback vertex set U, which size k minus p, and which is disjoint with feedback vertex set W. Right? Disjoint feedback vertex set in tournaments. Okay. So far, so good? Okay. Yeah. So in other words, I can rephrase it, right? What is the maximum number of vertices of X? I can add from here to here such that this path still will be acyclic. Right? This is, again, the same thing. Yes, and my claim, so this is the disjoint feedback vertex set in tournaments. Once again, I have one set and I have another set, and I ask if I can make a feedback vertex set which is completely disjoint from the one which I give to you. And my claim is that this problem is, again, solvable in polynomial time. This time it's a little bit more complicated. Why? This problem is solved in polynomial time. Well, I will use again the following fact about tournaments, which I kind of prove you that if my tournament has a cycle, it also should have a directed triangle. And the second thing is also quite simple, that if my tournament is acyclic, it has a topological order. What is the topological order of a tournament? I can order the vertices of my tournament from left to right, such that all arcs also will go from left to right. Right? And these things are equivalent. Tournament is acyclic, no directed triangles, and it has a topological ordering. And I really need all these three equivalent definitions. I will be playing with jumping from one to another. Okay, once again, so the first observation. Suppose I have a triangle in my tournament of this structure. Two vertices of the triangle, they belong to the set W, and one vertex belongs to the set A. I need to kill this triangle with my feedback vertex set, right? I cannot take any of these guys, right? Because these guys, by my assumption, they cannot go into the solution. So the only way for me to kill this triangle, unique way, right, is to take this vertex. I have to do it. No other way. Okay, this is what I do. So then, I go through these triangles added to my solution, decrease the parameter by 1. Okay, so what I know? So I know after I did this type of polynomial time preprocessing to my tournament, if I have any three vertices, two of them are from W and one of them is from A, then actually these guys, they cannot form a triangle. Right? Because if they form a triangle, once again, this vertex should go anywhere. Okay, what does it mean that these three guys, they don't make a triangle? It means that if I take this vertex and add it here, this is a cyclic tournament, right? So why this is tournament? Why this set induces a cyclic tournament? Because these guys, they anyhow they cannot go to the solution. So if this tournament is not acyclic, I say no immediately. Right? So if I add this guy to this tournament, it still should remain acyclic because there is no direct triangle here. One observation. But this means that if I take a topological ordering of this tournament plus this vertex, every vertex in the topological ordering of a cyclic tournament has unique position. So this means that all of these vertices, each of these vertices, it has a unique position if I add it to here. Okay, that's one thing. And now I want to define a specific ordering P. So what I'm doing here? So I have a cyclic tournament here, right? So this tournament induced by the vertices of A, it also should be acyclic, right? Because that was a feedback vertex set. So this is a cyclic guy, this is a cyclic guy, and I also know that if I add so this guy has a topological ordering. So and if I add this guy here, it still should have a topological ordering. So there is a unique for every vertex here. There is unique position here for this vertex. On the other hand. Yes, this tournament is also acyclic, so there is also topological ordering here. Let me call it Q. So I have one topological ordering and I have another ordering P. So then, and have another ordering here. So I construct an ordering P of the vertices of the tournament A. The following way. First of all, I look. I say that the P of U is smaller than P of V. What I'm doing is, first of all, this happening if the position of U, if I map it here, is smaller than position of V, if I map it here. But also it can be that that will be the same positions, right? Because I cannot map two vertices simultaneously. So for one vertex it can be position I, and for the second vertex it's also be position I. Then I compare these vertices subject to the ordering U of them. This is the second thing what I'm doing. And this defines me the ordering. And now, put everything happening here. So instead of finding a set of vertices here, which I can add and make this guy acyclic, so the only thing which I have to do, I have two ordering, or two sequences, and I should find the largest or the longest common subsequence of this guy. So why that should be enough? Because, well, first of all, if I add a set of vertices here, add it here, and they are acyclic, I can take a look at the topological ordering here. It should coincide, so all edges should go from left to right. So it should coincide with ordering Q, and it also should coincide with ordering P. Right? And other way around. So if I take longest common subsequence here, then all edges in this subsequence will go from left to right. And if I add the vertices here, I will still have a topological ordering, so I will have a cyclic ordering. Just think about this. Okay? But this is a polynomial time solvable problem, actually. Right? Dynamic programming will do the job here. So that's it. So so basically, so everything reduced to construction of the orderings and then or the sequences, and then I have to find the longest common subsequence of this sequence. And here I'm done. So this shows how this joint feedback vertex set is solvable in polynomial time. And which means that the compression part of the algorithm is also doable in 2 to the k polynomial time. And then this joint feedback vertex set, it means it's solvable in 2 to the k polynomial time. And once again, so when I do iterative compression of this algorithm, so I can solve a problem in time 2 to the k times time. So I already explained two problems, vertex cover and feedback vertex set. And obviously there is some common pattern. Let's just try to generalize or try to understand what's happening here. So if I cover, so basically what kind of arguments I was using already twice. So if I cover some problem star, and I have an algorithm which solving the compression version of the star in time f of k times some polynomial, then yes, then there is by applied iterative steps, I can solve the problem in time f of k, so n times c plus 1, right? I make n iterative steps. Now, so in order to solve compression problem for my star, compression version of my star problem, the only thing I have to do, I have to solve disjoint version of the problem. And then the running time will be, well, I do all 2 to the k guesses here, so the running time will be here. So yes, I go through all possible subsets, and then I run so the disjoint version on a smaller instance. And in particular, so for example, if I am able to solve my disjoint star problem in times alpha to the k, then I am able to solve compression star in times 1 plus alpha to the k. Yes, and my last example is a 3-heating set. So 3-heating set is a more general than a feedback vertex set on tournaments. And also, we know already how to solve it in 3 power k time. Let me just do iterative compression, what's happening here. Okay, so now I don't want to speak about iterative steps anymore, right? And I just, the only thing I want to show you how to solve disjoint problem. So, because if you solve disjoint problem, you solve compression problem, and if you solve compression problem, you solve iterative problem, and you solve the problem finally, right? So the essence is the disjoint problem. So what is disjoint 3-heating set here? I have heating set here of size k plus 1, and I ask if there is another heating set of size at most k, which is disjoint with this heating set. Okay. The first argument is exactly the same what's happening for feedback vertex set, right? If I have a set of size 3, 2 elements live here, 1 element lives here. Then I have to heal the set. I cannot use this people to kill the set, so I have to use this guy. And this is a unique choice. So these guys go to the solution, and what I'm doing, I remove all sets which contains this element from my solution. So I reduce the problem, Now, what I'm left with, right? So I cannot have a set which lives entirely here, right? Because this is a heating set. I cannot have a set which lives entirely here, right? Because that was also heating set. So every set lives, part of it lives here, part of it lives here. Now, with two guys of the set and one guy, so two guys of the set cannot live here. We already reduced all these guys. So the only case which is left when I have a set of size 3 and one guy is living here and two guys are living here. Where? In here? No, but this is disjoint, right? So I cannot. No one from here can go to the solution. So 3 guys cannot live here. And once again, all 3 guys cannot live here because that was the solution. Yeah. So this is exactly so. Every set should be partitioned by this guy. Okay. So this means that at least one of these guys should go to the solution. So what I'm doing? So the trick is the following. I just construct auxiliary graph. I build auxiliary graph, so the vertices of the graph are the elements here, and 2 vertices are adjacent if and only if they live in the same set. And then, what's happening here? I have to solve 2 heating set, or I have to solve vertex cover on this graph. Right? So in order to solve this joint heating set, I have to solve vertex cover, and for vertex cover we already have quite fast algorithm. Right? So you just take your favorite algorithm for vertex cover, solve it. So in order to solve this joint heating set, we solve vertex cover. Now we plug in the whole framework, and we have yes again. So if we have a disjoint algorithm, we use compression. Then compression algorithm can be solved in time 1 plus alpha to the k, where alpha to the k is the running time of the disjoint algorithm. So we have the following theorem. So if I'm able to solve vertex cover in time c to the k, then I'm able to solve the 3 heating set in times 1 plus 1 to the k. And even with our naive 1-3 branching, right, this is already better than 2 to the k, so this is better than 3 to the k. Yes, and if no problems to iterate or to think if you want to really to master the techniques, try to do cluster iteration in 2 to the k time. Then the feedback vertex set on undirected graphs, try to do it in 2 to the k poly n. But a caution, this is a not easy problem, so you need to think, or you have to get hints here. Also, this odd cycle controller, I want to kill all odd cycles in my graph, or I want to make my graph bipartite. Also, this type of algorithm, iterative compression, and again, it's not an easy problem. You have to think about this, but the reduction is very cute for the joint problem. Yes, and this one is easier probably. Try to do the heating set in running time 1 plus c to the k, where c to the k is the running time. You need to solve d minus 1 heating set. So finally, summing up. 2 basic techniques, but techniques are simple, but really basic. And basically, if you start working on any problem, the best thing to do is just to start from this technique, in my opinion. Some people will say do color coding. Yeah, to me it's more branching. So but we will see about color coding next also. Okay, so branching, and also I give examples for this type of techniques, iterative compressions, and if you want to read more, there's chapter 3 and 4 of the parameterized algorithm books, which will be delivered today, right? After lunch. Okay, so if you have any questions, I will have them. Okay, then you can thank me also.